So this should be a lot of fun. For the last example in Houdini Fundamentals Collection Volume 2, I'm just going to take a look at how we might work a little better with dynamic constraints. So here we've got a constraint being deleted if it interacts with a rigid body object. And you can see all the possibilities that might be present in whatever kind of dynamic simulations you might cook up. Let's start off by setting up this simulation. So we just have a few objects here, and I'm just going to pipe those into the DOPS network. So the first one is the boards, the wood of the bridge. Next, we'd have a ball that's going to drop on it. And we've got some of these steel pieces, and we can make our own steel as it goes into the simulation. So I'm going to put that in input 4. And here we have some constraints which I've already set up. I'm going to go into input 3 with that. Diving in, let's do an RBD packed object for the boards of the bridge. First context. Next, let's get the ball in here. So maybe a RBD object. Up input path. The second input index. Okay, there it is. Now, one thing about this ball is I wanted to give the bridge a chance to settle first. So I'm going to set the creation frame to something other than 1, maybe 5. So now the ball won't get created until frame 5. All right, now let's set up our constraints network. So that's going to be the third context geometry, and let's use a spring constraint. And I already set the name on those constraints to lowercase spring, and I'm just going to do a dampening of 200. Okay, so it settles pretty quickly. And here we are. So gravity, merge, rigid body solver, constraint network, and I'm going to give it a ground plane and merge it with the ground plane. And let's see what happens. Okay, so there we have it. And just so we can give the ball and the bridge a little bit more of a chance to settle first, I'm going to change the creation frame of the ball to frame 25. And notice it's not really respecting the curvature of these boards, and that's because the boards have some concavity in them, and right now Bullet isn't respecting that. So I'm going to turn on create convex hull per set of connected primitives. I had already done a convex decomposition as in previous examples for that, and now the ball should stick on the bridge pretty well. And here we have it. All right, so looking at this bridge, the first thing I want to do is chop it with a big steel blade. All right, so we're going to send some blades flying into this, and as they come in contact with our constraint, we're going to do a SOPS operation and cut the bridge. So for that, we would need a solver here, and we want a SOPS solver. And a trick I have to make this cook, because it's really difficult to work with sometimes, it can be very confusing. We have to be viewing the simulation and cooking the simulation to get the relationship between the previous frame here. In SOPS, that doesn't exist. So we have to be able to work in here and see the updates and force the cook updates from outside of SOPS. So the way to do that is actually, at least my trick, is to split the views and always get the simulation cooking on a view here. So I'm going to lock this viewport, and then we'll just call this constraint. Okay, I'm going to put that in here. And then diving in, now I'm going to use a null or an output and call it output. And I'm going to force the relationship geometry to cook by using an external SOP and just pointing it directly inwards. So now it's fairly ready to go, and also lock this view. So now, regardless of which one of these, or if we are doing something else in SOPs, it's always going to cook this, and the DOPS will always cook as well. Okay, so now let's set up our steel blades. So unlock this temporarily so we can set up our steel blade. Okay, so here's a piece of geometry, pretty simple, and we're just going to transform this into place. It's going to view the bridge here to see where it can chop. Okay. So I'm just going to move, rotate, and possibly scale this thing. Into a pretty good position. Okay. So as opposed to the ball where we could just set the frame number that we wanted to be created on, this we might want more than one blade. So I'm going to save the frame number to be created on as an attribute. And we can call this attribute just about anything we want. I'm just going to call it frame. And I'm going to set it to op digits so it's really easy to work with. So attrib frame, and let's have this thing be created on, I don't know, let's say frame 50. So down here, I'm going to go point integer op digits. Okay, actually maybe a primitive is better. Okay, and then downstream of this, we'd want to isolate that. And if we wanted any more steel blades, we would just merge more steel blades in. Okay, so primitives non-selected at frame equals the current integer frame. So if that worked, then what we have here is on frame 50, we just get one little steel blade to appear. Now let's set that up in DOPS. And RBD fractured object. I'm going to make as many steel blades as we want. So let's source the steel blade, op input path. And this will be, I believe, the third input or the fourth context. Okay, and notice it's actually not creating anything because it's not really going to create anything on frame 50 because we've set the creation frame to 1. So here, we would want to set the creation frame to the current frame. So that just means it's going to be setting the creation frame as we go. Okay. Now, it still didn't create anything, and that's because this says fracture by name. So we need to give this a representative name as well going into the simulation. So I'm just going to do another attribute create. And let's call this the name primitive string. And we can do steel underscore the current frame number. Okay, so now we'd be able to kind of have a little marker for what steel blade this was based on what frame it got created on. And there's more ways to mark these things as well. All right, blades. So putting this in and viewing our simulation. Okay. So we have a lot of action happening here, but it's not breaking these spring constraints. In fact, these constraints will never be broken in their default behavior. And now the interesting part is we're going to dive into the SOP solver here and program our own constraint logic. So in the SOP solver, first thing to notice is that these constraints will not be moving, even though we can see them moving here. And this is really just a visualization. To move these constraints around, each of these constraints has a name attribute on each point. So we can use the transform pieces and transform them according to our DOPS pieces. So first we have to get the correct DOPS pieces in. So here I'm going to use a DOP import. The DOPS network is going to be that, which points to DOPNet2. And I think what we're after is the bridge object. Okay, so object mask bridge. And we want to create points to represent objects. Okay, so that successfully merged in a point representation of each object, and there's the positions we're after. So now we'll do a transform pieces. Here's what we want to transform it by. Here's our pieces. Now, notice this is still what's cooking. We don't want to apply this directly to the solver. But now we have something really important, and that's the fact that we can actually spatially compute where these constraints are and apply our logic based on where they are in specifically relation to our blades. Okay. So now, in order to chop this thing, I want to really up-res the sampling here to get a good detection. So we'll do a resample. And let's get that pretty dense. Okay, that should work. And we're not really taking a speed hit from that. These operations are pretty light so far. Also, we want to import the blades. So that's going to be another DOP import. This is bridge. These will be steel. And what did I call this? It's steel underscore. Okay, so we want to merge everything. In this case, I want the geometry. Steel underscore star. So any blades we might throw in, we're going to get the blade in here. And now let's do a detection. Let's say, hey, steel, are you interacting with anything in here? And right now it's not, but if we find a frame where it is, maybe something like that, then we can do a group. Okay, so here's our geometry. Here's what we want to group the geometry by. I'm going to do a point group, call this kill, and it'll be a bounding region, bounding object, points only. So we've managed to catch this constraint. Okay, but I don't want to just delete this part of the constraint. It doesn't actually exist in the actual constraint anyway. I want to delete the entire constraint. So for that, we kind of need to tag this with an ID or an identifier of some kind. And because these constraints, all we really care about is that we catch whatever constraint it was at the current time step. I'm going to do an attribute create here, and let's just make an ID by the primitive number. So we'll call this prim ID, primitive integer at prim num plus 1. Okay, so now we have a primitive attribute that's designated a prim ID, and as we resample, that still exists, and as we do that, it still exists. Okay. So using a blast, I'm going to say non-selected points kill. Okay, so there's what we want to delete. And notice it has a prim ID of 41. Well, let's attribute promote this to a point so that we can do some matching, some attribute transferring and some matching. So from primitive prim ID to point, first match. Okay, so now it's a point attribute. Okay, so we know pretty clearly here what prim IDs we want to delete. And then way up here, let's do a attribute copy. And we want to attribute copy an attribute to delete it. So in this group, I'm going to make an attribute called kill. So attribute create kill 1 integer for true false. Okay, so we're going to copy that attribute onto this, more specifically this prim ID. Okay, so it needs a prim ID and a point here, and it needs a prim ID and a point here, and that has to match. So 41, it's going to match with everything that has a prim ID of 41 here. So we're going to transfer over the kill attribute, and if it transfers, it's going to be 1, match by attribute prim ID, and the attribute name is kill. Okay, so if it found it, it's going to be 1, and if it didn't find it, it's going to be 0. And then finally, I'm just going to blast away everything except for kill. So at kill equals 1, and points. Okay, so that should have deleted the constraint in question. And if you look at that, it's deleting the constraint that got touched. So if that logic works, then we're going to plug it into the output, and now let's watch the result. There we go. All right, pretty cool. Okay, and just to expand on this system a little bit, I'm just going to go up here to SOPs level, and let's make another transform and another frame number to release an even bigger blade. Okay, so let's make this go on frame 100. See how procedural this system can be. Here comes the first blade, and the second blade obliterates everything. All right. Now there's definitely other systems and other ways we can do this. For instance, the soft body dynamics, cloth, vellum, but this is just an example on how we might get it to work with rigid body constraints, and that lends itself to a lot of industrial applications like buildings and bridges and whatever we might have, actual very fine-tuned support mechanisms. Okay, so now let's get this geometry out of DOPS. So one thing I was wondering about for a while is, how do I get these animated constraints out of the DOP network? It's pretty straightforward with the DOP.io and the DOP import to get the rigid bodies out, and we've explored a few ways to do that in these examples. But here I actually want the constraints out, and maybe we want to do a vellum sim based on these positions, or maybe we want to trigger something else. It's going to happen like a break of a dust hit or something like that. So what's an easy way to merge it out? And here I'm going to use an actual object merge and go into the constraint network itself, because this will be variable. I want just all the constraints out. So diving in here, I want this guy, and this is a pretty good place to get the constraints from right here. And if we want these to inherit the position, because as I said before, they're not actually changing their position here, then we could do the transform pieces. So we're going to transform these pieces by DOP import, create points to represent objects by that. And now we can see that our constraints are moving along with the simulation. Thank you very much. This concludes our foundational exercises for Houdini Fundamentals Collection Volume 2 in rigid bodies. I hope you got lots of useful workflows that you can apply to much more advanced setups.